Welcome back again. Today we're going to take a look at characteristics of polynomial functions. A little bit about maximums and minimums and a few other little odds and ends, but nothing too tricky. So let's jump into the lesson. I'm going to start off with local maximums and minimums. You're probably familiar with the term maximum and minimum, which is pretty straightforward. Why don't we take a look at this particular function, which happens to be a quartic function or a function of degree 4. And we can see that even though the graph doesn't actually put the arrows on for me, it goes up forever in both directions on both sides. So if we want to state the the maximum and minimum for it, well, the maximum, this thing goes up to infinity on both sides. So its maximum is definitely equal to infinity. And its minimum is going to take place in occur in one of two places, I should say. It's either here or here, and I think they're the same anyway, because there's some symmetry in this graph. And it looks like it's a minimum of 10, I think goes up by 2, so that would be what, 16? Negative 16? So it will have a minimum of negative 16. That's pretty straightforward. I mean, you've been doing that since, well, definitely at least grade 9. Maybe grade 10. Yeah, whichever. Now, the part that might be a little bit new to you is this idea of local maximum and minimums. And it's basically not the extreme or total maximum for the entire function, but where they occur on short intervals. So I'm going to try and keep that graph on the screen as long as I can. And we have some local max and minimums. Basically, they're the same as the other ones, except, or at least two of them are the same. That one there and that one there. Not only are they absolute minimums, they are local minimums. But we do have one local maximum that did not occur before. And it occurs up there at x equals, looks like it's about 9.5. Give or take. Sorry, 9, because we're going up by 2 each box. So we can put down that the local max is equal to 9, and the local minimum are equal to negative 16. And I'm going to make a little note here. There's two of them, because there are actually one local maximum and two local minimums. The fact that the two local minimums happen to be exactly the same value doesn't change anything. There are still two local minimums. For locals, we don't consider the overall extremes, so we don't consider the infinity part, just where it kind of reaches max and mins, or basically think of it like a roller coaster. Where do you hit your high and your low points? That's pretty much all there is for local max and mins. Except to mention that, I guess, how will the number of x-intercepts just edit that part out. Just edit it out. Bye-bye. Okay. And not that it's directly related to local max and mins, but something we should look at is how many x-intercepts will an nth degree polynomial function have? Well, here we have a fourth degree polynomial. It's quartic. You can see that up there. And it seems to have, change color, 1, 2, 3, 4 x-intercepts. Is that just a coincidence that it's degree 4 and it has 4 x-intercepts? It is not. So as it turns out, a nth degree polynomial will have, and now this is the part that some people do mess up on a little bit, will have, I'm going to change color just to emphasize this once I get my pen back. Come on, pen. At most, an nth degree polynomial will have at most n zeros or roots. So why at most? Just to give you an example of a few. I'm going to just draw a couple other quartic functions on there because it's possible to have other quartic functions. And here's a quartic function that has no zeros, no roots. Here's a quartic function that has one root, two roots, three roots. This one is not symmetric, but they do exist. 1, 2, 3 roots. And then we could have 4 roots like the one that we've already seen. Sorry, 4 zeros. Roots, same thing. So an nth degree polynomial will have at most n zeros or n roots, but it could have less, anything down to 0. I will point out that technically an odd degree polynomial, so something that looks like a cubic, for instance, no matter how you draw this, because it ends up down there and up here over the extremes, so something like this, it will always have to cross the x-axis at least once. It's impossible to go from a negative to a positive without crossing the x-axis, at least for a continuous function. Okay, so nth degree polynomials have at most n roots, even down to 0, odd down to 1. This next part here is going to be very quick and painless because you've been doing this for many years, and that's finite differences, or as you probably know them, first differences, second differences, etc. So basically, I'm going to point out, just so I don't have to keep pointing it out, that the x values are all going up by 1s each time, so there's no tricks here. Sometimes you have to check a table of values to see if the x values are going up consistently, but we're just going to look at the y values. And we can see here that the first differences between each of these are 7, 7, 14 to 21 goes up 7, 21 to 28 goes up 7, 28 to 35 goes up 7. So this becomes entirely constant for the first difference. This one here, you don't have to draw these little arrow things if you don't want to, goes up by 1, and then 3, 4 to 9 goes up 5, 9 to 16 goes up 7, and 9. And then the differences between those goes up by 2, 2, 2, 2. So this is constant when we hit the second difference. Just going to point out here, once I actually change tools, if you notice, first difference, degree 1. Second difference, degree 2. Let's see if that stays consistent as we go on. All right, y equals x cubed. Let's see what these ones go up by. I think they go up by 1, 7, 19, 37, and 61. That's the first differences. Second differences go up by 6, 12, 18, 24. And then our third differences go up by 6, 6, and 6. So we get a constant when we get to our third difference. It's messy, but you can read that, sort of. Okay, so our third differences are constant, and it is a third degree polynomial. Starting to see a pattern here. Okay, I'm going to go out on a limb and guess that this fourth degree polynomial, y equals x to the fourth, is going to have fourth differences that are constant. Let's see what happens. Ooh, the numbers are getting bigger. So I think it's going to be 1, 15, 65, 175, 369. Those first differences. And then we go up by 14, 50, 110, and 194. Got second differences. Here we go up by 36, 60, and 84. As third differences. And fourth differences go up by 24, 24. And it's good because we only have two numbers to compare, but they are the same. So the fourth differences are constant. Okay, and from here on in, I mean, if you want to pause and try these on your own, you are more than welcome to. But if you fill them out, your numbers are going to be 10, 30, 50, 70, 90. And as predicted, since this is a degree 2 polynomial, these are going to be constant at 20, 20, 20, 20. And one last one to try. This should be 2, 14, 38, 74, 122. 12, 24, 36, 48. And predictably, our third differences are going to be 12, 12, and 12. One I didn't write over here, second differences. Okay, so basically for a first difference or finite difference table, all we do is keep going until we get a constant, and the number of differences that we have before we hit a constant, the first, second, third differences, determine whether it's a first, second, third degree polynomial. Pretty straightforward. I realize I say that a lot, trying to instill confidence in both myself and you. So here we can finally say if the nth differences are constant, the polynomial is degree n. Now you might be wondering, what happens if it's not a polynomial function at all? And the answer is the finite differences will never end up being constant. They'll do all kinds of different things. I think you maybe recall for exponential functions in grade 11, it's not finite differences, it's finite ratios, so you have to do the multiples. Anyway, there's other things you can do for other types of functions, but for polynomial functions, you just check out the differences. Okay, there are some homework questions at the bottom there. I am going to stop this video, and that's pretty cool because this was a very short lesson. Gives you plenty of time to try the homework questions. There is a challenge question there, and if you've got questions, we will take them up at some point in the future. Until then, see you later.